Refraction. Last week, what did we do? Of course, we did the chapter called light, which we began by going through the properties of light, and then a particular property called reflection. And reflection is the proper term for bouncing of light. Well, it can bounce regularly or it can bounce irregularly. Okay, we called it diffuse reflection and regular reflection, where if you have to find the angle of reflection or the angle of incidence, we call this I, which is the angle of incident. That means the ray just hit the surface. And we call this R, the angle of reflection, where the light actually bounces off, and where I will be equal to R. Okay, cool. And we did mirrors here. Very good. One of the examples of a surface where you have reflection will be mirrors, where you have regular reflection. Now here, I will also be equal to R, okay, because this I is equal to this R, and this I equal to this R, okay? They will always be equal still. However, you cannot see an image because they are bouncing off in different direction, not all rocking in the same manner. For example, if all of us in the morning, when you sing our national anthem and I'll say our pledge, we all say the same things, it will hear like a clear pledge or a clear national anthem. But we all sing our own songs, then we cannot find a proper sound or a song in those mix of songs. We don't know which song who is singing, so you cannot find a perfect song. Similarly here, if all of them are bouncing off in different directions, you cannot find any proper image. Where here you'll find a perfect image, where they do have some properties which we also learned last week, like whether they will be upright or inverted, they'll be enlarged or diminished, they will be up naturally inverted, also on so forth. That will depend on the surface, whether it's a mirror or it's a microscope, what do you call it, magnifying glass, depends. So it depends on the type of glass that you're having. Something called refraction. This is very because this concept will carry you to Sec 4 even, or Sec 5 if you're going to Sec 5 to your O levels. I'm hoping all of you can try to go to Sec 4 and not go Sec 5, because actually your chances right now, who does not understand that if you do well in Sec 2, you can go to Express. You can be pushed from normal to Express. Those of you who are normal, you know, those who have friends in normal, please let them know that today I just heard that you can move from normal to Express. Some of you don't even know. Of course, your teachers will be telling you a lot. Okay, you can save 1 whole year. Well, I would want that. Okay, so you can take your O level by Sec 4 instead of waiting for Sec 5. I can get out of secondary school faster, and you can go out with your friends and go to Polytechnic even faster. Then that makes you grow up and be a grown up faster as well. So those of you who have interest in going from normal to Express, you have to buck up and study really hard. It's not difficult, but you have to work hard. If you work hard, you save 1 whole year, rather than would you want to be still studying in a secondary school when all your other friends are going out of school. So that's your choice, right? You make a call right now. You're at the perfect age group to make a call. So whatever I'm saying, whatever your science teachers are saying is good, please take extra care and notice and go through your work diligently, and you will be able to get through the barrier of normal to Express. Okay, so refraction is the important topic, as you can see on the slide right now. And dispersion will be a small little part that we will do at the end of the lesson today. Okay, and as for going through the questions that you already did, how many of you actually tried the questions on the website? I'm not sure. You should have, like I said, try to be hardworking. These are little homeworks that we give you here and there. Try to get them done. Then you will be on par with everybody else. You see those students who are always scoring very high marks, they are not studying very hard. They're just doing their homework, okay, properly. Okay, because we teachers are helping you along the way to say, this work has to be done this weekend. Next week, we give you another one. Next week. So we, on a weekly basis, we are pushing you through to make sure you are ready for exams. But if you put no effort, then you have a backlog, then that's when you start suffering. So we don't want you to suffer. We are helping you along. Like, so I give you a work, you want to do, you help yourself. You don't want to do, then you don't help yourself. Okay, so refraction, as I asked you in the poll, many of you couldn't get the correct answer. It's not the bouncing, because bouncing will refer to the reflection which we learned last week. Okay, so it will actually bounce and come back. So it will actually bounce and come back. Whereas refraction will not bounce, will go through. Okay, so instead of bouncing, it will go through, because it's actually not a reflective surface. It's like a glass, or can be water, and so on. So what happens is the light actually goes through. So let me change the color a bit so you can see it going through. And what do you notice in the direction of the ray? It actually did not follow the original direction, which was supposed to be this way. Am I right? My dotted line shows that if the light had gone through in its original direction, imagine you're running, then you hit a wall and you still can run straight through. No, because you got hit, so you actually divert a little bit. So you actually change direction a little bit. And also, the process of running through sand or water or glass is more difficult. Therefore, it will try to get out by the fastest way and choose the shortest distance out of the glass. That's why it goes to the yellow line instead of sticking to the green line. So this bending of light, I'm going to go a bit slower today. If you do not get to the questions, it's fine, because I do have nearly 90% of you haven't done this in school and do not know what's going on in refraction. So I need to teach you. Okay, so it's not like the other chapters where you already know, let's go fast. So you need to go slightly slower and make sure all of you understand. Take this knowledge to school, and then you'll be better off than your classmates. Okay, bending of light, and this is the other word for bending of light. In science, we call it refraction. So when somebody mentions refraction, it means bending of light. Why does it bend? It's because it hits something that is harder to maneuver, harder to go through. Whereas the outside is what? The outside, it was traveling in air. Remember, this is light ray traveling in air, as opposed to traveling in glass. It's two different things. You travel in a plane, you travel in a boat, it's different, right? You run on the track, you run in water, is different. Imagine you're going to run and teacher says, who can run the fastest in class today? And you put up your hand because you know you can run very fast. Then your teacher continues to say, oh, we are running in the swimming pool. You'll be like, I'm not too sure about that. I'm not be able to run so fast in water. Then suddenly somebody else could be faster than you in water. Suddenly you're not the fastest runner. So to be able to travel in a new medium is a totally different thing. So this is called a medium. Let me use another color, a red color. This box here is called a medium, and this medium is glass in this case. And this medium has its characteristic of what? Refractive index, which we'll cover later. Because of its refractive index, means it's dense medium compared to air. Air is not dense at all. So imagine you run in air versus run in water. That's what I'm talking about. So therefore, bending of light as it passes from, there you go. The word is medium. The medium can be air, can be glass, can be water, can be metal, and so on and so forth. Okay, from one to another. So this one here is showing you a glass block. This is an example only. Okay, so now you got the green color arrow, which we drew earlier, but this is drawn by computer already. Earlier, I drew it. now is drawn in the computer, showing you that actually it bent. Let's redo this slowly so you know what we were talking about earlier. Remember, the first light was going in this direction. It's a dotted line. If it continued, it would have gone in the dotted line, but it didn't. It bent. And bent is called refraction. Now, what do you notice about I and R? Remember last week's lesson, I, R, normal, bouncing off. This is I, this is R, is equal. But today's lesson, you have I and you have R, but it doesn't look equal. Because if it is equal, then I would have been this whole thing. Because I is quite big. Is this thing. So let's say this is 40 degrees. This is 40 degrees. Am I right? However, it's not 40 degrees. You can see it's actually smaller than 40 degrees. So this R is smaller than I when light travels through another medium, and the medium must be optical just means lighter, denser. Denser means anything that is optically denser than air. Okay, air is the least dense in this case. So outside of the block is air and inside the block is glass. So it's optically denser, hence it will travel slower. So light travels, not only the angle changes, the direction changes, light travels slower also, just like when you run in water. So take note of this effect. Because it's slower, so you don't want to get out of this. Imagine you are running in water and the teacher says, get out of the water. The fastest person to come out of water will win. That means you run, you will choose. You see now, if you had chosen the white path, it will take a long time to get out, right? So that's why you choose the black path, the green path. It is shorter way to get out because you're actually traveling slower and you want to get out fast. Okay, simple. Don't worry if you are getting lost. You just try to play this video again when you're free tomorrow or this weekend, and then maybe you'll get it. Okay, you can think over these slides over 24 hours, no problem, no rush, no hurry. Okay, your teacher did not say learn refraction and come back tomorrow. Okay, so we have the final picture here because we have the third line. We have 1, 2 lines studied very well already. What's the third line? The third line here, this line is like, hooray, I'm free, I've gotten out of the water. Just like you, when you get out of water, now you start running. So how many of you have seen this track event? Okay, where they run around the track and then they jump over a hurdle and then they step into water and then they go. Okay, I don't know who introduced this kind of funny event, but when you jump over the hurdle, you fall into the water, your shoes get wet, it gets heavier, and you run very slow. And if there's a lot of water, then you're probably running very slow. And you want to quickly get out of water and run on land as fast as possible. So here you go. The light had to go through, it hit, and then it went through. It says, I had a tough time going through the glass, and then, hooray, I am getting out of the glass. So this is called the refracted ray. And finally, the one that is coming out, the third ray that we're going to do is the emergent, the one that is emerging out. Emergent ray. And we've got 3 names now. Okay, we've studied incident ray, number 1, refracted ray, number 2, emergent ray, number 3. And the cool thing is the emergent ray and the incident ray look very much alike. Going to see they are parallel. So let me use the colors so that you can see they are roughly the same angle. Because if you draw the normal here, the normal to the ray is same. Okay, but instead of I, we usually try to put E so that we know the difference, but I equal to E anyway. Okay, they are equal, but we want to know that this is the incident angle versus the emergent angle, so we know which ray we are talking about. Okay, it is results from a speed of light. Okay, remember I already introduced the concept of slowing down light actually is slowing down, as I have already mentioned about us trying to run in water. Same thing, we will slow, light also will find it difficult to run or travel in thicker materials compared to air. So because of this slowing down, that's why it changes direction and tries to get out fast. That's another explanation to refraction. Okay, so there you got the same thing, but you can draw things at an angle. Suddenly they change the glass block to another angle. Remember, we studied the glass block being in this orientation. Now suddenly they change the glass block to this orientation. You must become experts that whatever orientation they give, when the light hits, what do? You draw a normal. I always try to draw the normal in the white color. Normal is like that. Why this is 90 degrees. And what will happen? Now we have green color, which will bend towards the normal. Now, this is called bend towards the normal. Why? Because now you'll see this phrase being used a lot, because here is the original direction. The green is bending towards the normal. The normal is white in color. So we always say is bending toward the normal. Otherwise, you don't know how to draw the bend. We know it's bending, but you don't know how to draw the bend. You don't know how to draw. Maybe you go and draw this way, which is wrong, right? You only must draw bending towards the normal when it's going from optically less dense to more dense, which is the case we have up here. Usually from air to glass, air to water. Okay, optically less dense means to air, from air to glass. The bending will be towards the normal. Now, when does the opposite happen? When it leaves the glass. Now pay attention. Now you think, why is he talking about bending? Because now it bent towards, but once it reaches the glass here, so you know the green one is the correct one, right? Once it reaches here, we draw another normal to figure out how it will bend. So another normal is like that. And if the light had gone straight, it will have gone this way, right? But it will bend away from the normal because it's changing medium again. And this medium now is from optically dense to less dense, going back to air. So what I do is change this word, bend. This word will be changed to away from the normal. Therefore, it should do this, away from the normal. You see where the normal is in white? If it bent toward, it should come here, right? It shouldn't do that. It should bend away. So that's why this and this should be parallel. Okay, let me draw it accurately, like that. So basically, this incident ray and the emergent ray should be parallel. That's why here is parallel, and the earlier diagram also we saw, let me go back to that, is the blue and the blue are parallel. So roughly this is what you get when you talk about refraction. So this is the concept. Okay, like I said, pardon me because you guys are learning, so I need to go slower so that you understand the concept. And I also expect, like any new topic, things don't go in your brain like that straight. It will take time. So you need to be going through this again with your textbook, maybe tonight after this lesson. Maybe tomorrow you play the video again of this video and then run through with me as I speak, because this is being recorded, right? So it's being recorded. So it's run through with me as I speak to make sure you understand what I'm saying. Tomorrow it'll make a lot of sense. Next Saturday it'll make a lot more sense. 2 weeks later it'll make a lot more sense. And by the time you get experts already. So I think I am going to not maybe do so many questions today. Like I said, I can push the questions to next week. Then we can see how much you have learned. Results from change in speed of light. Okay. So everything that I drew earlier is represented here. Like I said, usually I take some time to draw with colors and all that. And then next one is just a slide to show you some of the labeling of the thing drawn perfectly without errors of my drawing, you know. Okay. So how many of you have seen your straw being bent something like this? Okay, put up your hand if you have. Or say yes or something. Okay, you have noticed your straw looking like that. Is it because something wrong with your eyes? Maybe you forgot to wear your specs. Whether you wear your specs or you don't wear your specs, you will still see this. This is due to the only this concept, because of this bending of light. Only because there are two types of medium here. Okay, you are in the air. The straw, half of it is in the air and half of it is in the water. So because of that, what you see, because of course we see with our eyes, so light travels from the straw to our eyes. So the light that travels from the air part to our eyes is clear, is straightforward, right? It just goes to our eyes. But coming through water, what does it do? It goes through water, through glass, then through air. Can you see? So to exit the container, to reach your eyes, it needs to go through water, it needs to go through this glass as well, and then it needs to come out to air, and then reach your eyes. So it goes through so many things. So poor light, right? The light has to travel through to get to your eyes. In this traveling distance it takes, it actually bends. So because we just learned that light bends in a different medium. So now you know why when you see it, it looks like the straw is bent. It's not the straw is bent. The light was bent, and then when you see it, you appears bent to you. Because everything we see is due to light. Okay, if light bend and come to you, then you see bent, and simple as that. Okay, and it's not all straw. The straw on its own, if I take it out of the glass, then it looks straight. It won't look bent. But because you put it in water, and that water is causing the bending, so you will see light bend, and so for your eyes, it will look like the pencil or the straw bent here. Okay, so similarly, this is the image or the diagram that you have to draw to tell your teachers how refraction takes place. So the pencil looks a little bent. So this is what you see, right? This is what you see, because it looks like the light actually comes from here. Okay, because you believe the light is traveling straight and coming here, but actually the pencil tip is over here. Okay, this drawing is a bit not easy to draw. We are talking about virtual image and real image, so I will do this slowly at another time. Okay, so, but it's just for you to take note now. Okay, maybe next week we will go in detail on how to draw this. Again, if somebody is going to look at the fish, because she sees the light is already bent, so what we perceive is as though the light is coming from here. So what happens is we thought the fish is here. Understand? So humans think the light is straight. Okay, humans think the light is straight because we understand light travels in straight line. So we see as if it's a virtual image. It's not really there. The real image is here. The real fish is here. Okay, because it bent and came out, you think, the fish is there, but it's not. Okay, this is another effect of reflection. We will see things where they are not supposed to be there. Now, will this fish look bigger or smaller? Because Charmaine asked for this previous slide, does the pencil look bigger or smaller? Not really, right? It should look the same, but there may be some distortion because of the light traveling through the medium of water and glass. There's some distortion which makes it look bigger. Yes, it's possible because the ray of light is distorted. Okay, the light is distorting the image. So you're getting some haziness. So when you get some haziness, it's not sharp. So you find that the object doesn't look clear. So it looks slightly bigger. It's just like you take off your specs. Okay, you take off your specs and you look at the TV, or you look at the number, or you look at the bus number. Suddenly looks bigger. It's not bigger, it's actually hazy. So your 5 is supposed to be like that on the bus, right? But because it's not sharp, so you have some haziness, am I right? Around the words, around the alphabet, or around the number. So don't you think that will make it look bigger? Yeah. So that is why it looks bigger, but it's not actually bigger. It's because the image is distorted. So I'm going through so many effects of refraction showing you the fish and the pencil and the straw, because these are the effects in real life. We have to understand and realize why we're studying this refraction in detail. So similarly here, now if this boy wants to catch the fish, he will see the fish at this position. So he's going to throw some stone or sphere to catch the fish, he will aim this fish, but he won't catch the fish. Why? Because the actual fish is here. So if you understand refraction, what will you do? Doreen, Celeste, Azhar, what will you do? How will you? Because you already know physics, you already know science, you already know how things appear when you look at water. So you go to the beach, you go to the swimming pool, you see an object. Okay, you see a goggles, you put a hand in, you try to catch it, you can't, because you are trying to catch the real image. What must you do? You must put your hand in slightly lower than where you saw it. Then you will catch it. Got the idea? So it won't change to higher, left, right. It just lower, it's always lower because of the way light acts and bends over here. The bending is over here. Got it? How do we know there's a real image, Doreen? Because if you saw a fish, there is a fish inside there, right? If you saw a pencil, there is a pencil there. It's just that the position is wrong. Okay, the position. For example, the straw, the position is wrong. The pencil, the position is wrong. The fish, the position is wrong. But the fish is still there. Okay. Same here. It could be any object. Okay. If you do not see an object, then there's nothing there. If you see an object, then where did the object image come from? You can't prove it because you are, then I will say you are imagining things. Okay, there are some students asking me, can you prove that there's an object? What I'm trying to say is there is an object because you saw it. But I'm saying what you see is not in the position. The position is false. Object is true. And then you still ask me how you know object is true. Because you saw it. This person saw it, you saw it. You go to the swimming pool and you saw the goggles. Don't tell me suddenly you say, I saw a fish inside the swimming pool. You can't change the goggle to a swimming pool, right? I mean to a fish, right? So whatever you see is what you saw, but the position is lower. How do you prove that the position is fake, Doreen? Okay, based on this slide. Because like I said, the position is fake because if you try to throw a spear or try to catch it, the position is fake because try it. Next time you go to the swimming pool, you put your goggles in as it's going in, you try to catch the goggle. You won't be able to. So that's how you know the position is fake. Because what you see is not what is true. Okay, try it, then you will believe it. And the reason is we have proof that the light ray travels differently inside water versus outside water. And therefore, when inside and outside, there is a bending. This we learned, right? The first few slides. Remember this? We learned that there is this bending. Because light is going to travel in a denser medium. Number one, therefore it's going to slow down. Therefore it's going to bend. Therefore what we see is not true. Okay? You will get the hang of it as we have more examples. Don't worry, Doreen. Okay? So now you just need to find out where is the real image, where is the fake image, like Doreen likes to say. It's a fake position. Where is the fake position? The fake position where the object is called a virtual image. Okay, it's virtual. That means it's not really true. The other one is real. The opposite of virtual is real. But we don't call it fake. Fake is just for us to talk about it. But in science, we say virtual, meaning it's not really there. Just like last week, we talked about mirror. Mirror, right? The object that you see, you know, your hair, your nose, your beautiful eyes, you can't actually capture it. You put your hand into the mirror, can you capture yourself? You can't. It's just a virtual. It looks like it's there, but it's not there. It's a reflection, right? Because you think light is going in and coming out. Is there a possibility where light ray can go in to all the way to another Celeste or a Doreen inside the mirror and come back? No. It's actually bouncing off the surface. But we imagine and we think it's behind. So whatever we think, we feel is true, is not true, we call it virtual. The real person is you, it's outside. Okay? What if you are in the water? Will it be the same? As long as your eyes are outside the water, it's different. If your eyes are inside the water, it's different. So, if you're underwater, that means your whole head inside water, and you want to catch the goggles, then it's fine. There's no case of water versus air, right? Because you're inside the water. Your eyes is the one that playing the tricks. So, it only depends on where your eyes are. Okay, Azhar? It depends on where your eyes are. Now, for all these examples, the eyes are always outside of the water. So you're going to play with air and water. So it's like air versus water. Air is doing something, water is doing something. It's confusing you. Whereas if you are inside the water, it's only water. Water versus water won't confuse you. Got it? Okay. So we are only talking about medium to medium travel. So light also the same thing, is confused. It's going from air to water to glass. It will bend, play tricks with your eyes. But if you are inside, that's why when all of us are in air, it won't play tricks with your eyes. You see your laptop in front of you, it's not playing tricks with your eyes. You see your clock next to you, it's not playing tricks with your eyes. But if you throw this laptop inside water, that's where you're playing tricks with it. That's why when you have a fish tank, then all your fish are playing tricks with you. All the plants are playing tricks with you. That's why some of you who have aquariums, right? When you try to change water and all that, you try to put your hand in, you take the plant out. You have to actually go deeper than you thought it was. Try this also, okay? Those of you who have pet fish and all that, you have ever cleaned a fish tank, you will know, or you can go and check it out. You think, hey, I can take the plant from here, but no, you actually got to go deeper because the actual plant is lower than you think it is and that you can see. Okay, that's for refraction. Okay, half an hour of refraction done. Very important. These are the concepts. Okay, how to do the questions, how to draw the diagram, all slowly. Okay, don't hurry. Next week we have more practice. Take these concepts in first. Those of you who have already done this in school, it's also a good practice to listen to me because it's not an easy topic. Many students have a lot of questions. That's why even quiet Sec 1 students like you guys or Sec 2 students like you guys are asking me so many questions today compared to the last 3 weeks. Why? Because this concept is not easy to absorb. By us telling you that it's virtual, by real, then there's light, there's bending, there's diagrams. And drawing is even more difficult. Today, the whole day, Ali has been drawing everything. You haven't started drawing yet. Imagine you start drawing. You probably get lost. You don't know what to draw, where to draw, what line to do. All this, I will teach you. Okay? As long as you join me next week, we will do the drawing session together, slowly, step by step, to make sure you are as good as me. Okay, deal? Must be as good as me. Then you are fine in your school already. Okay, like I said, all of you have so many questions. Doreen and Celeste and Haza and Hazel. Everybody has been sending me questions today. Shamin. Okay, very good, because you are thinking. Okay, the moment you're asking question means you're thinking. And I'm also happy with myself because I'm not too fast today. Going so slowly to make sure all of you absorb what I'm trying to say. To get some questions is good, so that whenever you ask, I answer. Then you're like, oh, okay, thanks. I now understand. I understand. Then, like I said, tomorrow or day after, play this video again and just go one more time this video. And then by the time you get to school on Monday, you are like super good in this chapter. Next week, you'll meet me on Thursday. We go through drawing. By then, we see how good you are. Don't you all want to be good in one topic at least, or especially the most difficult topic? Once you're good in the most difficult topic, what are those easy topics, right? Not too easy. Okay. White light is a mixture of different colors. Now, this is very easy. This one is something that all of you have been playing since primary school, since kindergarten. You know the colors of the rainbow very well. You've seen a rainbow reflection in the sky. You've seen rainbow reflection in your home. When there's a small slit in your home, when light travels through the slit, it actually splits up into 7 colors. And sometimes on the wall, you see the 7 colors of the rainbow. So rainbows are not only limited to the sky. It's not only limited to the sky. You can see it in your home too. Whenever light splits, because light is colorless, you actually cannot see, but we call it white light. When they're combined together, it's white light. And if you split them, they split into the 7 colors, which is what happens in the sky, in the rainbow. How that happens, we need to explain using science concept. So that's dispersion. So what you're exactly seeing as a rainbow is a result of dispersion of light. Okay, versus what we did today, refraction of light. What we did last week, reflection of light. Wow, you guys are like experts really. Finish this, then today now do dispersion. And the very first poll that I did earlier, okay, maybe I'll launch the poll again because I have more participants. Relaunch polling. Now let's see whether you all can answer. Guys, make sure you do know what we did today. We did bending of light we did bouncing of light last week. You can change your answer. We did bouncing of light, which is refraction, last week. Then we did bending of light today, which is refraction, right? Then we're going to do separation of light, which is dispersion, which is separate the white light into its different colors, which is dispersion. So all these three options have their names. The first one, bouncing of light, is reflection. The second one, separation of light, is dispersion. The third one, bending of light, is refraction. Okay, so if you can change your answers, you're allowed to, then I can close the polls. Are you allowed to change answers? I'm not sure. Because some people still. Okay, so let's share the result. Without sharing results, it's no meaning. Okay, the orange one is the one that won the most votes. That's correct. So most of you understand that the word refraction refers to the bouncing of light. I know, the bending of light. Okay, bouncing is last week's lesson, and then the rest separation. Nobody. Okay, good. Okay, so let's put down what we just learned. Here, bouncing, bending, separation. Okay, and you all are really interested in this lesson. And then you already asked, Celeste, you are asking me what causes light to split. Okay, what causes light to split? As you know, light just is a ray, right? Okay, what happens is if you have a surface with very tiny holes, okay, then you'll come through, you'll try to split. But what actually happens is not really tiny holes. Let's say we have to tie our lesson back to the medium. Okay, so now let's say this is a different medium. This is air. This is different medium. Okay, so let's just work with one light. So white light, how is it split? Remember, when white light comes in, let's draw it in white. Okay, let me do it slowly so you all can appreciate. White light, when it comes in, okay, it shouldn't come in at the normal, right? It should come, okay, let's say it comes in this way. And then you draw the normal. Normal is just a line perpendicular to the surface. So what will happen to the light? It will bend. Very good. Because the different medium, so it will bend. What color is this light? Red. What color is this light? Orange. What color is this light? Now, because individual colors have their own characteristics of wavelength and speed, so when they slow down, they're like, they come to a break. Why? They hit the different medium. White light was traveling very fast from, let's say, from the sun. Remember, they all come out from the sun also, right? Light comes from the sun. So they travel very fast. And the moment they hit a medium like this, be it water or glass, what happens is they are blocked. There's a medium to block. Now it has to travel differently. Remember, all of you run very fast, then suddenly there's water. You jump into the water. Now in water, when you start run, are you running together already? No. All of you run differently. Some people very heavy in water, run slowly. Some people can swim in water, wow, go very fast. So red light, orange light, yellow light, green light, blue light, indigo light, all of them will travel at different speeds according to their ability, according to the characteristic wavelength and speed. So because of their different speeds, the they will what? Bend at different angles like this. You see, not all bend equally. If all bend equally, then it'll be like that, then it'll be like that. Okay, let me just show you white color. Okay, if the light came in like this, then it'll just bend like this. Finish. I don't see any splitting. However, that's not what happens. Because white light was made up of the different colors. That is red, orange, yellow, and so on. So when they come in and hit, they will slow down according to their own ability. Just like when you, as a class, goes into the swimming pool, different people swim differently. So that's why they will split in such a way. So can you see what happens to the colors? So next color will be ROY, G. Suddenly, what do you see? Suddenly, what you saw as white is seen as different colors. It's, oh my God, I see a rainbow, right? You get excited because the colors have started splitting. One class became many people. Okay, all of you inside one class, the bell ring, tring, recess only, all of you split, right? Go to your own canteen, own shop, sit with your friends. Then you still ask me, sure, how the light splits? Then I ask you, sure, how my class splits during recess? Same way, right? Each one of you have your own desired characteristic. The way you split is how light splits, because they want to go in their own speed, own direction. So that's how light splits. Because why? The fundamental reason is they hit a different medium. So therefore, here is glass, can be water. So when do we see rainbow then? Do we see rainbow every time? Every time is air. So the light keeps coming out as white. I see the sky now is white. When is the day I see the rainbow? The day it rains. The day there is water in the sky. There's water content. There's a lot of water. Be it clouds, be it the rain drops. So when it hits this amount of a lot of water, so the water splits the light. Yes, you can force a rainbow. I have questions from Doreen say, can we force a rainbow? Yes, we can. If you try to let the light in through a small hole in your door or your glass window one day, and try to see. The hole must be very small, and it must be, the sun must be shining out there, right out there brightly into your window, and because of it's hitting the glass, right, it will split the light into 7 colors, because there's glass and there's air. Okay, just try it. If you can't, then maybe next week we try to see a video. I'll try to show you a video how to force a rainbow. Ken, next slide. Actually, I wanted to show you how to force a rainbow. Okay, how many of you have seen CD-ROMs? Disc. Okay, this is a CD-ROM. Because they have little tiny grooves, the CD-ROM looks like this to play songs, and they have a lot of lines. So if you have a lot of lines, and then light falls, and then when it bounces off, it actually splits into its 7 colors, because again of the line. So this, we call it a dispersion. Okay, this is another example of dispersion. Okay, there you go, we got rainbow. Lights of different colors bend by different angles as they leave the prism. So you can force a rainbow. Who asked me the question? Doreen. Doreen asked me whether you can force a rainbow. Yes, by using the proper equipment like a prism, because a prism is not a glass block. A glass block, why? Because a glass block goes in, and what happens is white light goes in, then it splits, but it's not really split much. See, I am drawing the different colors, but do you see it split much? Not really, because the angles are too little. So they are still combined the same color, and you still see the white sometimes. Not enough. So you change to a triangle where it's a prism. So when it enters here, it splits, okay, here. So that this is the normal, if light is coming in, it will split. And then when it goes out, it won't go out in the same direction. It will go out in the, you must draw, okay, let me draw for you properly. Yeah? Okay, and you've got normal, and you've got the white light goes here, it will bend towards the normal, and then you will have another normal, and you have to bend away from the normal. So what happens, light that actually came here will actually go out this way, unlike this one where the light comes in here and is parallel. So that's why in a prism you can definitely see the split more clearly, because they will not rejoin back. You can see the split more clearly. All right, so prisms help to split light, and if you want to combine them back, you have to use another prism like this, and you can combine to get back the white light. Okay, Charmaine, you want to see previous slide? This is my previous slide. Okay, some of you just giving me random requests. Okay, so I'm just accepting your request and just going to follow, because I take myself to be like in a class. If I'm in a class, if somebody asking questions, say go back to the last slide. Of course I'll go back. Okay, I must try to be as real as possible. So Charmaine, I don't know if this is the slide that you want to see, or is it this one? Okay, this one. Okay, so prisms are one way to force the rainbow. Okay, and there's another way, is also using Newton's discs. You paint the disc in all the 7 colors, and then you spin it. When you spin it, they spin so fast that actually you can see white. How many of you can try? You can color this, and then you put like a string on both sides. You hold the string, and then you just do turn, and then you pull it, right? It'll just spin very fast. How many of you have seen? Just go and find for this word Newton's disc on YouTube. Go to YouTube. See how people do the Newton's disc. Okay, and you'll see people, kids. Doreen has tried, but it doesn't spin. Okay, maybe you have to improve on your experiment. Okay, maybe you should get a proper cardboard that spins fast, and then you have to paint the colors as true as possible to the colors that are of the rainbows, and then you will see that magically it does become white. That is the answer to all of our questions, that white light is made up of these 7 colors. But we don't need to doubt it, because we've seen our rainbows all our life. So nobody can say no. All right. So final, before we end today's lesson, dispersion is how we see things also. When we see a red apple, we see red because light bounces off it. Okay, what light bounces off it? The light from our ceiling, the light from the sun bounces off it and reaches our eyes. What color reaches our eyes? Only red. What about the other colors? What happened to orange, yellow, green, blue, indigo, violet? It got absorbed by the apple. Okay, so here I go. Let's draw an apple. Maybe I shouldn't even draw it as red. I should just draw it as just like that, no color. Okay, so what happens is white light from somewhere, there's a source. Obviously, if there is no white light at all, what happened to the apple? It will turn black. What do I mean by black? It means can't be seen. Imagine you off all the light. Remember at night you're going to sleep. You put one apple next to you. Make sure there's no light, no curtains are drawn, no light source at all, no phone, nothing. And you put the apple next to you. Nobody can see the apple. They probably step on the apple, because apple has no light to bounce off to show you as even red color, or even if it's there. So light is important. So you switch on the light, white light hits the apple. What happens is, you are standing trying to see the apple. What happens is a red light comes to you. Remember, white light had all these colors. Am I right? But only red light travels to your eyes, making the apple look red in color, because you saw red. What question is, what happened to the other 6 colors? That's the property of a red object. The other 6 colors will be absorbed by the apple. Only red color is reflected off the apple. That's the property of the apple. That apple. If another apple is green, then green is reflected, and so on and so forth. Whatever color your object reflects is the color that we see, because our eyes is not a magical being. It depends on light. Only with light we can see. Without light, you cannot see. Can you? Right now. So that's why we depend on the light. So light, whatever it shows us, we believe. Whatever it does to us, our eyes will take it as a. So when the light falls and it shows us red, we say it's red. When the light falls and shows us green, we say it's green. Our light. So our colors will depend on the reflection and the absorption. So you need to know what colors were absorbed, what colors were reflected. Questions will come up where I see a green tree. Why are the leaves green in color? Okay, then let's do that. So a leaf is normally just no color probably, but then we see it as green. So green is reflected to our eye. So we see it as green. So whatever light came in, which was white in color, is what? The 6 colors are absorbed. So again, 6 colors are absorbed. So this one is very important. What is the real color of an apple? The real color. Okay, very interesting question, right? Now you all are starting to, hey, how come light bounce, then we see a red? Then what's the actual color of? Everything has no color. The color is based on the color it reflects. Okay, everything originally has it, and the absence of light has no color. That's why I say the apple in a dark room is no color. You want to know the color? Doreen asked me, what's the real color of apple? You go and put inside a dark room and see that. Do you see it as white? Do you see it as black? Or do you see it as no color, dark? Yeah, I think probably it's black. Black is the universal no color color. Like you go into the outer space, right? Space is everything. There's no color, so it looks black, right? And you go into space. The moon is surrounded by black color. So I think probably the answer to your question is black. What determines the color is the property of the object to reflect. Okay, this is my mouse. Okay, this is my mouse on my table. All of you can see. What color is it? Black. That means this color, this object cannot reflect any color. It absorbs all the colors. When white bounces, it doesn't even allow red to be reflected, doesn't even allow white to be reflected, doesn't allow, you know what I mean? So if it's white, what about our white paper? Okay, what is this? This white paper. What color does it reflect? How come it's white? White is not part of the rainbow, right? So answer me, all of you answer me. What color does this white paper reflect? Is it red? Is it green? Is it yellow? Or all the colors? It does not absorb any color. It reflects. So color is determined by the property of reflection and absorption. That's all. Celeste asked me this very important question. Celeste, you said, then what determines the color? The color is determined by reflection, absorption. If all colors are reflected, I will see white. If no colors are reflected, all are absorbed, I will see black. If only red is reflected, I will see red, and so on and so forth. Okay, this also takes some time to absorb. It's okay, just store it into your brain. We come back to it soon. So does this picture make it clearer? Does picture make it clearer? Okay, I think you can. Now, there are many questions in your mind, and you guys are very smart. I really love it that you guys asking questions. It's really interesting because you are involving yourself. Doreen asked me another perfect question. What about color blindness? How does it affect? So now this person is colorblind. So how does it affect his ability to see colors? Why? Exactly because the apple is not red. The apple appears blue to him. Why? Because of his ability to not able to detect red in his eyes. So color blindness is that you cannot detect a certain few colors. So everything looks another color that your brain perceives, like it looks like blue. So what is red to you? Colorblind person. The person is colorblind because his eye has a defect that cannot distinguish between red, green, blue, black, white, whatever. So he mixes up the color. So he thinks blue light is coming to his light, to his eye, because his eye cannot see red. So different like that. Then there's, so this one you can go and read about it more. Okay, go and type Google color blindness, and you can read exactly how somebody's eye works, such that how come they can see a red color in blue. We can research this more. Okay, this is beyond the scope of our lesson, but at least you have questions. You are understanding the lesson very well. Good. So object will appear as the color it reflects. Okay, this has also been drawn for you earlier. What did I draw? If red light is reflected, you will see the object as red. If you only, this center diagram is important. Let's say you shine a green light, you don't shine white light. Center one, let's all focus on the center one. This kind of question can put you off in the exam. You'll be like, hey, this one I never learned before. Because you are not shining white light. White light has all 7 lights inside. That is different. Then you can see who is absorbed, who is reflected. But this one, you're only shining green light. But green light is absorbed. Remember, for a red apple, green light is absorbed. So actually, an object will appear black. That's why, for example, you are in a room here, we all use white light to see things. Can you imagine if you started putting green light in your house? All of you just have green light. Then a lot of your things will look black. Those objects that actually absorb that green light will look black to you. You get the idea? So it's a very unique concept for you to think through. Okay, that's why we don't use colored lights. If you go and use a colored light in your house, then the colors of the objects around you are all going to change depending on the bouncing off and the reflection. Okay, take note of this, but it's okay. As we go through the questions, we will figure out a lot more. Okay. Lastly, beneficial effects of light and harmful effects. Okay. Of course, light helps us to see, but light also can affect our vision, can even make us blind if there's too much light. Okay. And good. Who asked me the question about color blindness? Doreen. Thank you so much. Celeste, you said, can you make a material or object specifically observe a reflect color? Yes, you can by painting it. Remember, a paint does that same thing. When you paint something red, you are actually telling the object to appear red. That means you are telling the object to absorb all colors, which means the paint that you buy from the shop, the red color paint, absorbs orange, yellow, green, blue, indigo, violet. It only reflects red. So actually the paint has that characteristic. So painting is a way of making things look the color that you want it to be. That's why we paint our walls. So the wall, you take a green paint, it appears green. You take a red paint, it appears red. Why? Because it's absorbing the colors from your light in the room and showing you only the green. Okay, that's one answer. Then Charmaine asks, why does the blue light from the screen make our vision worse? Remember I said, when they run in the water, they all have their characteristics, okay? So blue, compared to all the other colors, okay, affect our so-called vision, right? We have cornea, we have iris. So that color has been shown to damage our ability to see the most. So that's why we try to remove the blue light factor from all our screens, because actually our screens originally were built to give us white light. You see, if you see a screen, it doesn't appear green, doesn't appear blue, doesn't appear red, right? But over time, we figured out that we go and test, we go and put somebody in front of a blue light, in front of a red light, in front of a green light, or in front of a yellow light. And over time, they see that our senses, our eyes are most damaged when we are exposed to blue color. So what they did, okay, let's try it more. Let's try people with more blue, more blue, more blue. And with more studies, they confirmed that blue light is actually the worst. And they said, no wonder people get vision worse from a lot of exposure to the computers, because computers actually give out a lot of blue light as well. So what they did, slowly, they want to protect our eyesight. They remove the blue light part, and still your screen can be seen without blue light. You still have 6 other components. That's why when your phone, okay, this is my phone with me, you can put blue light filter, right? So it will block the blue light, but suddenly my screen doesn't look as bright. Why? Because the blue light, green, all contributing to what you see here, but the blue light factor is removed. Okay, so you try to protect your eyes. Okay, what about the colors that are not included in the rainbow colors? They are probably a combination of other colors. Those of you who go to art class, they are actually a mixture, okay, a mixture of other colors. So that sums up today's lesson, and I want you to take this knowledge to go and try the questions which I had, okay, directed you towards in the homework section. Some of you did, some of you didn't have time, never mind. This weekend, since I've managed to excite you about colors, and you are more than eager to find out what are the questions they can ask us about reflection. Is that fisherman really going to throw a spear at the fish and try to catch the fish? There are questions like that. And there are colors. Are we really going to make colors forcefully appear as a rainbow? And so on and so forth. So these questions are interesting to solve on your own. And then we see each other next week to solve them together and we get a better idea. Deal? Can or not? Now time for dinner for all of us. All right, some of you already had dinner, then it's better for you to go and have a rest before school tomorrow. And then weekend is here. And please, 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 for the sake of me, to thank me, please try a little bit of those questions before we come for class next week. It's only about, 10 of you here. Hopefully we can share a lot more fruitfully than today, because today was really nice, right? I can actually have time to read your questions and answer you one by one. And I'm sure you feel happy if I answer your questions. So try to get me more questions. See you next week. Ta-da. Love you guys. Bye.